Hello, my name is Alex Panchula, and today I'm going to be discussing energy from the sun. First, I will be discussing the solar irradiance principles, including the inverse square law. Then I'll discuss very briefly the figure of merits for incident solar energy. In addition, I'll be talking about factors affecting the incident energy. I'll also touch on the diurnal or the seasonal pattern of the incident energy. It is important, of course, to start with the sun when discussing photovoltaics. And there are two measurements at the Earth's surface that we want to consider. One is irradiance, and the second is irradiation. Irradiance is the power per unit area, whose units are either watts per meter squared or equivalently kilowatts per meter squared. Irradiance follows the inverse square law. So if we're twice as far from the sun, we would only get 1/4 of the irradiance. Irradiation, on the other hand, is power per unit area in time, or energy per unit area, which is of course very important when considering energy generation at the Earth's surface. The units on irradiation are watt-hours per meter squared or kilowatt-hours per meter squared. An example of the difference between these two units is the average irradiance of a clear sky day would be 600 watt per meter squared for 8 hours. The irradiation for that day is the product of 600 times 8 hours, or 4,800 watt-hours per meter squared, or 4.8 kilowatt-hours per meter squared. The inverse square law states that the irradiance is reduced in proportion to the inverse square of the distance from the source. In the figure, one sees that plate B would receive 1/4 of the irradiance that plate A would when it's twice as far away from the sun. The inverse square law is important because it defines the solar constant for the Earth. Light incident at the top of the atmosphere of the Earth at a distance of 1.5 times 10 to the 8 kilometers on average has a power of 1,366 watts per square meter. This is the Earth's solar constant. If we look at, for example, Mars, at roughly 1.5 times as far from the sun, you would divide the Earth's solar constants by 1.52 squared and only get 591 watts per square meter at the top of the Martian atmosphere. This is important, I guess, if you're designing a Mars rover, but it's also important for PV designers to understand that the total amount of energy on average is really limited by this sort of Earth solar constant of 1,366 watts per square meter. The other important point to note is that all extraterrestrial radiation comes straight from the sun. That is to say, it is direct beam radiation. There are multiple ways that insolation is reported. Insolation can be measured as an average, in which case the units are kilowatt hours per day. It can also be summed, in which case the units are kilowatt hours per year. Both of these are shown in the figure as a world map. It's also important to know that there are different measurements of insolation. A typical input for a flat panel PV application is global horizontal insolation. This is the measurement of the total sunlight that would impact a flat plate sitting on the ground at the Earth's surface. Another measurement, which is used in concentrating applications, is direct normal. This slide shows the clear sky model demonstrating seasonality. If we look at the global horizontal area, which is the blue area, we see that the total irradiance peaks in the summertime at around 1,000 watts per square meter and has a minimum in the wintertime of around 600 watts per square meter. The diffuse horizontal, which is a component of the global, is more or less constant under clear sky conditions at around 100 watts per square meter for this location. The red area is the direct beam, which again is used for concentrating applications and not for flat plane PV applications. Up to this point, I've been referring to global horizontal insolation. Next, I want to introduce the concept of effective irradiance. Effective irradiance is the light impacting on a surface inclusive of all optical gains and losses. This is really the first step in energy conversion to determine the amount of useful light hitting the module. For example, for a flat plane PV application, the module could be tilted or tracking the sun, which would result in a larger irradiance than that global horizontal. In addition, there can be a series of losses. You could have losses at the horizon due to mountains. You could have shading reflections. You could have loss due to soiling on the surface of the module, or you could have gain or losses due to spectral changes. The effective irradiance is always referenced to the 1 sun standard spectrum, which is defined as 1,000 watts per square meter and the AM1.5 spectral standard. The first step in effective irradiance is calculating the gain due to tilt or pointing the module at the sun. This can result in significant gains of total irradiance over the GHI or global horizontal insolation. In the upper right-hand figure, this is an example of a calculation where multiple sheds are being tilted, and the gain of 12.5% is achieved at roughly a 30-degree tilt from horizontal. One of the important losses that can be attributed in also the direct beam is losses at the horizon. Buildings, mountains, trees, anything in the distance that can block the sunlight from reaching the modules can also be accounted for in many energy prediction software programs. For example, a mountain is drawn on the red line on the lower left-hand graph, and this blocks the sun, particularly in the winter time, where each of those curves is a sun path during different times of the year. Of course, it's not just faraway objects that can cause shading, near objects can as well. Many PV applications have many rows of modules, and at least during some times of the day, there's direct beam shading, where the shadow of one module impacts another module. Typically, the electrical impact of such an effect is actually greater than the area impact, but fortunately, energy prediction software can calculate this quite accurately. The other thing to note about near shading is that just because a shadow does not appear in the module does not mean that that module has a clear sky view. And it is possible for a module or other object to block the diffuse component of the light, which is also important for energy generation. Reflections from the ground can also provide additional energy for PV modules. This is typically parameterized by a single value called the albedo. The upper right-hand figure shows the albedo for different types of ground cover, snow, desert, cities, etc. And there's a strong interplay, of course, between shading and reflections, because for space constrained, where the modules are very close together, there's a very small impact of albedo on the total energy generation, whereas if you just had a single row of modules, this actually might be a much larger impact. Soiling and snow losses are also important for calculating effective insolation. Dirt and snow can reduce the amount of light impacting the modules, which of course reduce generation. This is a highly localized phenomenon where one place on the Earth would not be the same as another, and typically, especially for snow, is a very seasonal impact. It's very difficult to make general statements about soiling and snow losses, but they are important to consider. Atmospheric effects are also important to understand. Light, for example, can be reflected by clouds, and very short spikes in irradiance of greater than 400 watts per square meter have been observed. In addition, seasonality due to water, ozone, other aerosols, pollution, for example, in the atmosphere can cause seasonal energy yield changes. One common measure of some of these atmospheric effects is a concept called air mass. Air mass is the length of the path that the direct light takes through the atmosphere. This changes, of course, over the course of the day as the sun rises and sets, but also changes over the course of the year as the Earth revolves around the sun. This is really a first-order estimate of the spectral effects that can happen in the atmosphere, and typically the larger the air mass, the redder the light is. The official spectrum is the ASTM G173 reference spectrum. People refer this as air mass 1.5 or AM 1.5, and it's still commonly used, although maybe slightly incorrectly. If we look at the solar spectrum and the effect of the atmosphere on the solar spectrum, we see a number of things. As the light travels through the atmosphere, it can be scattered or absorbed or reflected, and this creates not only our blue sky, but also horizon brightening and clouds, it also creates a series of absorption bands. And these are shown in the figure and labeled by the chemical constituents that's creating the absorption band. So for example, H2O are all the water absorption bands, and O2 and ozone are listed as well. And you can see there's a difference between the yellow spectrum, which is the sunlight at the top of the atmosphere, and the radiation at sea level, which is shown in red. And you can see that those significant absorption bands are really one of the major differences between what happens at the top of the atmosphere and at sea level. One of the advanced topics I'd like to cover is something called spectral mismatch. Each of the constituents of the atmosphere impact the energy available to the module. So, for example, the absolute air mass is shown in the upper left-hand graph, and the spectral mismatch factor for a number of different PV technologies is shown. And you can see that not all technologies respond to air mass in the same way. In the lower left-hand corner, we have the response of these technologies with precipitable water. Here, one could see that, for example, the CAD-TEL module in green has a much larger spectral mismatch factor with respect to precipitable water, which is to say that the more water in the atmosphere, the greater the relative performance of a CAD-TEL module over, for example, a crystalline silicon module. The last topic I would like to discuss today is measuring the sun. And I've included a quote from the Best Practices Handbook from NREL where it states, in part, measurements of solar radiation are among the most uncertain in any measurement discipline, which is to say, measuring the sun is hard. The state of the art for solar measurements is pyrheliometers and shaded pyranometers on two-axis trackers, where separately the direct beam and the diffuse irradiance are measured. These systems are fairly costly and difficult to maintain. What is more typical for PV installations is to use broadband thermopile pyranometers, both global, which is to say flat, and in the plane of the array. Also, rotating shadowband radiometers are sometimes used, and more recently, side-by-side reference modules are used to measure both the spectral impacts and also the effect of soiling. Some of the devices for measuring the sun is shown in this slide. Pyranometers measure global irradiance, where this can be either flat, in which case it's measuring the global horizontal, or in the plane of array. These are thermopile based, which means they are also broadband, measuring from 200 to 2800 nanometers typically. Pyrheliometers offer a very narrow view and measure direct radiation only. They are typically pointed at the sun, requiring sun trackers, which results in that higher upkeep I mentioned earlier. In addition, reference cells can be used, which can be spectrally matched to the PV modules you use. These have fast response, although typically they're not as accurate in terms of their total irradiance measurement. Also, rotating shadowband radiometers are useful for measuring separately the diffuse and direct components. What these typically use are silicon cells that have these very flat responses, and a small bar basically blocks the sun for a very short period of time, and the ratio between the total sunlight and just the diffuse component can then be calculated. So in summary, I'd like to review some of the concepts. We discussed the difference between irradiance and irradiation. I discussed the different units of measure of insolation. I introduced the concept of effective irradiance and walked through some of the common gains and losses to achieve the effective irradiance. And finally, I touched on measuring devices of the sun.